Now we're going to explore some properties of logarithms that are actually based on the properties of exponents, because recall, a logarithm is nothing more than an exponent. So let me start by just giving you a few things to think about. I have a few expressions on the screen, and I want us to make some observation between the expression in the first column and the expression in the second column. In the first row, I have this expression, log of 10 times 100. So if we simplify the argument of the log first, 10 times 100 is 1,000. And what is the log of 1,000? Well, that is, what is the exponent that 10 must be raised to get 1,000? And that is 3. In column 2, now I want us to simplify log of 10 plus log of 100. Well, the log of 10, what does that mean? Right, what? The power of 10, that gives me 10, and that is 1, right? 10 to the 1 is 10. Plus log of 100, what do you think that is? 2. Good job, because that is the exponent of 10 that gives me 100, and that is 2. Well, 1 plus 2 is 3. So these two expressions give us the same result. This means that log of this product, 10 times 100, is the same thing as the sum of the logs. That is, log of 10 plus log of 100. In my second row, I have the log of this quotient, 1,000 divided by 100. If we simplify the quotient first, 1,000 divided by 100 is 10. And what is the log of 10? Right, it is just 1, because 10 to the 1 is 10. Now what if we compare it to this expression? Log of 1,000 minus log of 100. Well, log of 1,000 is the power of 10 that gives me 1,000, which is 3, minus the log of 100 is, you got it, 2, and 3 minus 2 is 1. So we can conclude then that log of this quotient, 1,000 divided by 100, is equal to log of 1,000 minus log of 100. And then this last row, I have the log of 100 squared, and I want to compare it to 2 times the log of 100. Well, if I simplify the log of 100 squared, I'm going to square 100, which is going to give me the log of 10,000. And so what exponent do I need to raise 10 to get 10,000? That is 4. And then what if I compare it to 2 times the log of 100? Well, this would be 2 times log of 100 is the exponent of 10 that gives me 100, which is 2. And 2 times 2 is 4. So I can see that the log of 100 squared is equivalent to 2 times the log of 100. And so I'm going to make some official properties relating to these specific examples, right? This is just an example of some properties that we'll make in just a moment. But notice that I have the log of a product is the same thing as the log of each of those factors added together. So that is, the log of a product is the sum of logs. The log of this quotient is the same thing as the difference of the logs of the numerator and denominator. And then the log of an exponential expression is the same thing as that exponent times the log of the base. So the first property is the product property of logs, and it is for b, x, and y positive real numbers with b not equal to 1, the log to the base b of the product xy is equal to log to the base b of x plus log to the base b of y. This is stating that the logarithm of a product is the sum of the logarithms of the factors. And this follows from the product of like basis property of exponents. Recall that b to the m times b to the n is equal to b to the m plus n. And let me show you that here. The other properties and this property are actually proved in the text, but I just want to go through it briefly. So let's say that m is going to be equal to log to the base b of x, and we're going to call n log to the base b of y. And what we know, just by definition of the logs, if m equals log to the base b of x, that tells us that b to the m is equal to x. N is equal to log to the base b of y is equivalent to b to the n equals y. Well, now I need to figure out what is the log to the base b of xy. So if we look at this log to the base b of x times y, well, what is x times y? It is b to the m times b to the n. So this is really the same thing as log to the base b of b to the m times b to the n, which is equivalent to log to the base b of, well, when I multiply like basis, I add the exponents to get b to the m plus n. And so what is log to the base b of b to the m plus n? Well, we just talked about this with the inverse properties. We just get m plus n. Well, what is m plus n? It is log to the base b of x plus log to the base b of y. So that's the mathematical proof that gives us this property. I'm not going to expect you to state that on a test, but I do want you to have some understanding of where that comes from. So now we're going to have an example where we apply the product property of logarithms to rewrite some expressions. And we will want to assume that the variables represent positive real numbers so that our logarithms are defined. The first example is log of 100y. So I would notice that the argument is a product. So based on the product property, I can rewrite this as log of 100 plus log of y. Right? The log of a product is the sum of the logs of those factors. Well, log of 100 is 2 plus log of y. We just keep it. The natural log of 4e, again, my argument is a product, so I can rewrite this as the natural log of 4 plus the natural log of e. The natural log of 4 is some decimal. Natural log of e is 1. So I can just rewrite that as natural log of 4 plus 1. In part C, I have the log to the base 2 of x plus log to the base 2 of x minus 5. So this time I have the sum of logs. I want to apply the property in the reverse direction. If I have the sum of logs, I can rewrite this as the log of the product of those arguments. So this is equivalent to the log to the base 2 of the product x times x minus 5. And I will put that expression in parentheses to denote that the x times x minus 5 is inside the argument of the logarithm. Now the quotient property of logarithms states that if I have b, x, and y positive real numbers with b not equal to 1, log to the base b of x over y is equal to log to the base b of x minus the log to the base b of y. And this shows us that the log of a quotient is the difference of the logarithm of the numerator and the logarithm of the denominator. This follows from the quotient of like basis property of exponents. You remember that if you have b to the m divided by b to the n, that is equivalent to b to the m minus n. And let me just back up for a moment. When I was proving the product property, if I instead said log to the base b of x over y, I would have log to the base b of b to the m divided by b to the n, which would be log to the base b of b to the m minus n. So I would see that I would get that equal to m minus n, which is a difference of the two logs. So it's not a hard stretch to follow from the previous proof. So let's see how we can apply this. So again, the log of a quotient is a difference of the logs. And if you can just think about all those properties of exponents when you're simplifying these expressions, it would really help. So I want to apply the quotient property of logarithms to rewrite each expression. And again, I'm assuming that the variables are positive real numbers. So the log to the base 7 of z over 49. So my argument is a quotient. By the quotient property, I can rewrite this as log to the base 7 of z minus log to the base 7 of 49. And then I want to simplify this to rewrite as log to the base 7 of z minus, well, 2, right? 7 squared is 49, so the log to the base 7 of 49 is just 2. The natural log of e divided by 5 would be equivalent to the natural log of e minus the natural log of 5. Well, the natural log of e is 1 minus natural log of 5. Log to the base 5 of a minus log to the base 5 of 14. So here I have a difference of two logs. I can rewrite it as a log of a quotient as a log to the base 5 of a over 14. And then the last property is the power property of logarithms, and it is for b and x positive real numbers with b not equal to 1 and r a real number. Log to the base b of x to the r is equal to r times the log to the base b of x. This is going to be a really, really important property that we apply quite often in solving exponential and log equations. So this says when our argument is an exponential expression, I can bring down the exponent to be a coefficient of the logarithm. Now this property comes from the power property of exponents that says b to the m all raised to the n is equivalent to b to the m times n, right? When I have an exponential expression raised to another exponent, I can multiply those exponents. So this property states that the log of a power is the exponent of the power times the log of the base of the power. In example 4, we're going to apply the power property of logarithms. Again, we're going to assume that all of our arguments are positive and logs are defined. If I have the natural log of x to the 3, this is equivalent to 3 times the natural log of x. So the power or exponent comes down. The log to the base 2 of x plus 3 to the 5, because my argument is an exponential expression, I can rewrite this as 5 times the log to the base 2 of x plus 3. Log of 5 to the x, I can rewrite as x times log of 5. Log of the cube root of x, I have to do some work on this one to recognize that the cube root of x is the same thing as x to the 1/3. So because I'm taking the log of an exponential expression, the power property says this is equivalent to 1/3 times the log of x.